This video is an introduction to the HTCondor ClassAd language. While users and administrators can be very productive with HTCondor without understanding the ClassAd language, using the language effectively is a key step to moving from a beginning Condor user or administrator to an intermediate one. The ClassAd language is a powerful tool, and once you get the hang of it, it's kind of fun to work with. So let's get started. One of the first commands that any HTCondor user or administrator learns is CondorQ, and if we ran it, it might output something like this. It emits about 8 attributes for each of my jobs that is active in the queue. It is probably not a surprise to anyone that HTCondor keeps much more information about jobs than just these 8. But in order to fit on a screen, we choose to display these 8 attributes by default. We hope that these are the most important attributes that people care about most of the time. There are a few options to CondorQ that make it show a different set of attributes. For example, the CondorQ-hold option displays information relevant to jobs that are in the held state. While this is useful and good to know about, clearly, HTCondor can't make an option for every single possible display that you might want. And that's where ClassAds come in. One of the easiest things you can do, once you know just a bit about the ClassAds language, is to display the attributes you are most interested in. Before we get to that, we need to learn just a little bit about how CondorQ works under the hood. CondorQ works by querying an HTCondor schd. The schd holds all the information about active jobs in the system. Active jobs are ones that haven't completed yet. This information is stored in an HTCondor ClassAd, one ClassAd per job. When you run CondorQ, it asks the schd for all the ads for that user. And the schd responds and sends the ClassAds, one ClassAd per job, containing information about the jobs back to CondorQ. When CondorQ gets the ads, it then decides how to print them. In the default case, if you pass it no command line options, it prints one job per line with just those 8 attributes per job. If you want CondorQ to show you the full ClassAd for a job with all the information that Condor knows about it, you can pass the -L for long option to CondorQ. As the name implies, this tends to generate a lot of output, so it is often prudent to get long information about just one job, as I've done here with the CondorQ-L on job 180. This is what a typical job ClassAd looks like, or rather, part of one. The full job ad would be way too big to fit on this screen. As you can see, the ClassAd format is pretty straightforward. It contains a set of attributes, which CondorQ has printed one per line. Each attribute has a name on the left-hand side before the equal sign, and a value, the text after the equals. We'll call these the attribute name and the attribute value, or the name and the value for short. You'll notice that the values can be of different types, strings, numbers, and other things. If you know the attributes you are interested in, you can use the CondorQ-AF option to show just those attributes, one job per line. This is especially useful when run from scripts, as we may change the format of the default CondorQ with no options to look better in the future, or maybe to show different attributes. Those changes might break a script trying to scrape CondorQ output. CondorQ-AF, though, is guaranteed to be stable over HTCondor versions. Also, when you use -AF, the schd only sends the needed attributes, so it can be up to 100 times faster than CondorQ-L. Your script may not care about performance too much, but the schd tends to be the bottleneck on many Condor installations, so offloading work from it is always a good idea. The values in any HTCondor ClassAd attribute are expressed in some units. For example, the disk usage attribute in a job happens to be in kilobytes. And the remote user attribute, which shows the amount of user CPU time this job has consumed on a remote worker node, is in seconds. If you aren't sure what the name of an attribute is, or what it means, the HTCondor manual lists all of the available built-in attributes, their units, and their usages in its appendix. Please visit it at htcondor.readthedocs.io. There's a big table in the back of the manual that looks something like this. There's all kinds of good information here. We recommend you look at it often. One big power of ClassAds is that you aren't limited, though, to these predefined attributes in the manual. The ClassAd language is extensible, which means that you can add custom attributes to your job that have meaning only to you. To add custom attributes to a job, you can use the plus syntax as highlighted in this slide. Just add a plus followed by a ClassAd attribute with the legal ClassAd syntax in your submit file. The plus sign is what tells Condor Submit that this line is in the ClassAd language, not the submit language. It is particularly important to note that the ClassAd syntax is just a bit different than the general submit file syntax. For example, strings like blue here need to be in double quotes in the ClassAd syntax, but are generally unquoted in the general submit file syntax. Once this is done, you can define custom ClassAd attributes. You can use them without any difference between built-in ones and the ones you've added. So you can use Condor Q-AF with your custom attributes, just like any other attribute. As such, we recommend that users add these kinds of custom attributes where they help you understand more domain-specific information about your job. So, if you want to define your own ClassAd attributes, or just understand the existing ones, you'll need to know their syntax. Let's get to that now. Every attribute has a name. That's the part before the equal sign. Names must begin with a letter, then can have letters, digits, or underscores thereafter in their name. ClassAd attribute names are case insensitive, but traditionally we use camel case, meaning that we start with a capital letter, and every new word in a compound name also has a capital letter. A best practice for naming when defining your own custom ClassAd attributes is to use some common prefix followed by an underscore in all of your names. That way, it is easy for humans to pick out your custom attributes from the standard built-in ones. Also, it avoids name collisions if Condor happens to pick your name for a future built-in ClassAd attribute. There are 5 main types of ClassAd values, or the thing that goes after the equal sign in a ClassAd attribute. Booleans, true or false. Integers, which are always signed quantities. Reals, which are floating point values. Strings, which are just a set of characters. And references, which are kind of like variable lookups. Let's look at each of these in detail. Booleans are the simplest ClassAd value type. They are either true or false. Please note they are never quoted and always case insensitive. In this example, the attribute named exit by signal has the Boolean value false. ClassAd integers are always 64-bit signed quantities, even on 32-bit machines. Again, a pretty straightforward type. In this example, Condor cluster ID, disk usage, and queue date are all examples of ClassAd attributes with integer values. Remote user CPU is not an integer because it's got a dot in it. Remote user CPUs is a real value or floating point. These are stored as 64-bit floating point, so have tremendous range. For the mathematical programmers, these do support positive and negative infinities, as well as not in numbers, but you'll probably never run into those. ClassAd string values are always enclosed in double quotes. If you need to embed a double quote character within a string, it can be escaped with a backslash in front of it, but that's the only special character you get inside a string. Please, don't try to put a new line inside of a string. Most of the HTCondor tools and daemons cannot process those, and you'll likely get kind of a strange error. Perhaps the most common error when working with ClassAds is to forget to quote strings. If you don't, you most likely won't get an error, but a very surprising failure instead. If you don't quote a string of characters on the right-hand side, you get a ClassAd attribute reference, or reference for short. This is like a variable lookup or indirection. Using our example job add, if we ask for the attribute request disk contains an attribute reference, note the lack of quotes, to disk usage, which is looked up and returned. So, if we ran the command Condor Q-AF request disk on this one job add, the result would be 100. Well, this may not seem too useful in our simple example. We'll see later how powerful this can become. As the old saw goes, any problem in computer science can be solved by adding one more layer of indirection. And here's our indirection. There's one final value that we need to talk about to complete our tour of ClassAd values. And this is the undefined value. A lot of people seem to find this confusing, which is a shame, as it really is a very easy concept. I've found that often, the more experience people have with other programming languages, this experience throws them off, and as most other languages do not have this concept of undefined, and experienced users trying to map this onto another concept is a mistake. Quite simply, undefined means I don't know. Any attribute can have the value undefined, and it means the system knows that it doesn't know the value. It doesn't even know the type. So an attribute that has the value undefined, we don't know if that's true or false, or even a Boolean. It could be a string or a number or whatever. We just don't know what it is. And this honesty about what we don't know is particularly valuable in a distributed system like HTCondor. Please don't think that undefined is an error or exceptional condition. There are many common times in HTCondor where a value is expected to be undefined. What are some reasons HTCondor might have an undefined attribute? Well, maybe Condor doesn't know the value yet. For example, maybe we don't know the CPU usage of a job that hasn't started. Or maybe we can't know the value. Perhaps HTCondor is running a job on a remote system that can't measure the CPU usage. Or maybe we are querying an attribute that was newly added to Condor, and the version we happen to be running isn't new enough to support it. All of these things can cause undefined values. We need not to worry about this, but we should accept things we don't know and plan accordingly. The explicit syntax for undefined is pretty rare. It's just the word undefined, case insensitive, and again, not quoted. In our example job ad here, we see the exit by signal attribute is explicitly undefined. Maybe this means the job hasn't exited yet. Maybe it means it's run on a system without Unix signals. We just don't know. It's undefined. But the more common case we find undefined is when the attribute is missing. In our example ClassAd here, now the attribute exit by signal is missing. And if we ask to display it, we also get undefined. There is no way to tell if an attribute is undefined because it is explicitly set to undefined or if it's missing. And that's by design. Keep in mind the fact that there is no difference between something explicitly undefined and something missing means that typos also show up as undefined. If I ask to display the Q date from this ad, which happens to be the Unix timestamp when it was submitted, I get a reasonable answer. But if my finger slips and I mistype the attribute name, I get undefined with no indication of an error. So be careful. With that, we've covered the important ClassAd value types. Even with the oddities of undefined, it's all pretty straightforward. Let's move on to see how we can use these values in the real world. Returning to our first example, some of you may have noticed something interesting going on. The condirq-hold command displays different ClassAd attributes than the default condirq. This shouldn't be surprising. In particular, it shows the hold reason. But the eagle-eyed among you may have noticed that it does something else. It doesn't show all of your jobs. It only shows a subset of your jobs, just the jobs which are in the hold state. As I've shown with ClassAd tools, you can choose to display some of the attributes of jobs, a process we call projection, using the -AF option. As we haven't shown yet, you can also choose to display only some of the jobs. We call this a constraint or a selection. Of course, you can do both at the same time. Projection with AF is useful for display, but selection is the basis for most of the policy and configuration mechanisms inside HTCondor. We use it to tell HTCondor to select which jobs should run where, what machines belong to what users, and many, many other cases. Most of the rest of this talk will be about selection with ClassAds. To demonstrate how to select a subset of job ClassAds out of a larger set, we will first need that larger set of ads. So we'll run condirq-l to get all of my job ads in the long format. And the output might look something like this. Obviously, this is cut down quite a bit in order to fit on the slide, but here we are showing 3 job ads separated by asterisks. We'll use this display for a set of ads for the next several slides. The option to constrain the output of condirq to a subset of the jobs is called -constraint, which takes a Boolean argument, like exit by signal in this case. We can abbreviate constraint to const, which is typical and makes the command fit better on the slides. What const does, it goes through each ClassAd in the larger set, one by one, and checks to see if the argument to the constraint is true. If it is true, then it prints out the ad. If there's also a -AF option, it only prints those attributes for the ad. In this case, condirq-constraint exit by signal would only print out one ad, the ad for cluster ID 181, as it is the only one whose exit by signal is true. Now, the question you should have in your head every time you use ClassAds is, what about undefined? we know that any ClassAd attribute can be undefined. So what happens when exit by signal is undefined? In this example, we've made the attribute exit by signal undefined in job 182. This is done in the usual way, not by making it explicitly undefined, but by removing it entirely. As you should remember, this means I don't know. Exit by signal could be true, it could be false, but technically it could even be a string, whatever that would mean. We just don't know. With undefined, it is always up to the program or the user to decide what that means. And in the CondorQ case, or generally with selection, we try to err on the safe side. So selection or constraint always assumes that undefined means don't select, just to be sure. So when we run this CondorQ, we only get job 181 again, as it's the only one where we are sure that exit by signal is true. In the general case, though, the argument to dash constraint isn't just an attribute name which has a Boolean value. The general case is a ClassAd expression. An expression is several values, connected via ClassAd operators, together resulting in a Boolean value. An attribute name, which has a Boolean value, like the exit by signal, is just the simplest case of an expression. This expression language is similar to C, Python, or other languages, so it should be familiar to a lot of people. And because expressions frequently have spaces in them, we need to protect those spaces from the shell. So it is very common to put the whole expression inside single quotes, at least on Linux. Before we dive deep into the syntax of expressions, let's take a peek at some common examples of constraint expressions and what you can do with them. This shows all jobs whose main executable is MATLAB. Note that the main executable is called CMD in ClassAds, which the manual would tell you. It would also tell you that CMD is a string, so it goes inside double quotes. This one shows all jobs who have been preempted and restarted more than 10 times. And this one shows all jobs whose CMD starts with the letter F and have exit with a signal. Clearly, these expressions have a lot of power to them. Now, let's dive into the syntax a bit more and see what we can do with these expressions. The first way we can build up expressions is by putting one of these logical operators between two ClassAd values. Or, instead of a value, these logical operators can go between some larger ClassAd expression. These operators should be pretty clear. They generally return either true or false, depending on the operator and the operands. For example, greater than returns true if the first operand is greater than the second operand. I hope that by now, everyone watching this video has cultivated the little ClassAd voice inside their head saying, what about undefined? What does, say, 7 greater than undefined return? Well, if we just go back to our definition of undefined, it means I don't know. So, is 7 greater than something? I don't know what that is. Clearly we don't know. Could be greater, could not be. And we have a way to express this uncertainty in ClassAds, undefined. So, 7 greater than undefined is itself undefined. We just don't know the answer. Generally, any logical operator that has an undefined on either side returns undefined. However, there are some exceptions. And returns true if both sides are true. If the first side of the and is false, we know that the expression returns false, no matter what the second side is. So, as a special case, false and undefined is not undefined but false. This is because no matter what the undefined may be, anding it with false will always be false. And the opposite is true for or. True or undefined is true. Equal and not equal when operating the strings, as a special case, is case insensitive. And we'll get more to that much later. Now let's run through some quick examples of logical expressions. To make the output easy, I'll add -AF cluster ID, so we just show the matching job IDs. Let's select all job whose command is sleep. We can do this by running CondorQ-const command == sleep. Again, make sure to put strings like sleep inside double quotes. Command is an attribute reference, which is looked up in each ClassAd and returns the value of that reference. This should select jobs 180 and 182. And here we show how to use greater than with numeric values. This selects all jobs whose disk usage is known and is greater than 100. And it should select jobs 181 and 182. Putting the previous two together with an and, this will select jobs whose command is sleep and whose disk usage is greater than 100 kilobytes. That is, just job 182. Moving on from our logical operators, ClassAd also supports the usual complement of mathematical operators, with the expected semantics and operator precedence. Parens can also group operations into the needed precedence you need. Note that these only work on integer or real types, not Booleans or strings. As you should expect by now, if either operand to a mathematical operator is undefined, the result is undefined. And here's a quick example of a mathematical expression in action. Disk usage is stored in kilobytes, so if we divide it by 1,000, or is it 1,024, we'll get megabytes, and we'll try to select those jobs whose disk usage is greater than 5 megabytes, which selects job 182. The ClassAd language also supports several dozen built-in functions. I've listed a few of the more common ones here. Check the manual for the full set. Some of the commonly used built-in functions include time, which returns the current time in seconds in Unix epoch format, substir, which returns a substring of the input, and the very useful regex, which returns true or false if the regular expression string contained in the first argument matches the expression in the second argument. Here's a very common pattern we see with the time built-in function. This query returns all jobs who were submitted to the queue more than 3,600 seconds or 1 hour ago. Depending on what time it is when this query runs, this may return all, some, or none of the jobs. Going into any detail about the syntax of regular expressions is well beyond the scope of this talk, but ClassAd uses the PCRE regular expression format, which has extensive documentation online. The ClassAd regex built-in function allows ClassAd matching to work with regular expressions, as in this example. Note that the regular expression itself is a string, so it must be double quoted, like in a string. The argument in this case is an attribute reference, here the CMD attribute, the command attribute, in each job. Also note that the value of the command is a string, bin sleep in this case. The double quotes in the display tell the human that this is a string, but these double quotes aren't stored in the ClassAd internal format. Because of this, when we try to match, don't try to match the quotes. They aren't in the internal format. And when you run this, we should get all the jobs whose command starts with the letter M. The final ClassAd function I would like to talk about has to do with undefined values. The built-in function is undefined, takes an expression as its argument, and returns true if this expression was undefined. This is one way we can make decisions about undefined attributes. In this case, we're going to print the cluster ID of all jobs whose command is undefined. And when we run this, we should get job 182, which somehow has the command attribute missing, which again means undefined. ClassAd expressions are, as the name implies, an expression language. This means that they always evaluate to or return one single value. However, sometimes you want to return different values based on different inputs. This is where the control flow expressions come in handy. One common use is to check for undefined and to turn it into some defined value. There are two different syntaxes in Condor to do this. The question mark colon, the so-called ternary operator, which takes an expression before a question mark and, if true, it evaluates it and returns the second expression. If it isn't true, it returns the value of the third expression. Or you'll see the if-then-else function, which does the same thing, but with a function call like syntax. This example may be a bit contrived, but it does show the ternary operator at work. If CMD command is undefined, we return true. Otherwise, we return true only if the command is MATLAB. And if we run this, it'll return job 181 and 182. And here is what that same query looks like with the if-then-else syntax. There's no preference really, but you'll tend to see both in ClassAd's code. And this use of checking if something is undefined is so common that it leads us to a special operator, the question mark colon operator. Other programming languages have something like this operator, and they call it the Elvis operator. I guess if you turn your head to the side, it is supposed to look like the famous pompadour haircut that Elvis Presley wore. I don't know. But what this operator does is take an expression on the left-hand side that may be undefined. If it is undefined, we evaluate and return the expression on the right-hand side. If the first expression is not undefined, we just return what it evaluated to. So we could rewrite the previous expression like this. Note that if CMD is undefined, cmd double equal MATLAB will be undefined, and we'll take the second part of this expression. But if it isn't undefined, we'll just evaluate and return the first part. Note that the precedence of the Elvis operator is maybe not what you might expect, so it is generally good practice to put the whole thing in parentheses. And, as Elvis has left the building, that just about finishes the main discussion of the ClassAd language. For the next part, I'd like to show how these basic concepts are used throughout HTCondor. Up to now, we've focused on manipulating the active job ClassAds held in the schedD by running the CondorQ command. But HTCondor jobs are not the only entity in the system which uses ClassAds. Almost every other entity in HTCondor is represented by a ClassAd and can be queried and manipulated in very similar ways as we've seen earlier with the CondorQ command. Not just the active jobs have ClassAds, but also historical jobs, jobs which have left the queue. The slots on machines where jobs have run are also represented by ClassAds, as are the users and accounting records. This table shows the commands to run to get the long form of any ClassAd of the type in that slot. Just like with CondorQ, each of these commands can also accept a -AF option to project out only certain attributes. They all take a -const or -constraint option to select a subset of ClassAds of that type. Of course, job ads have attributes relevant to jobs, and machine ads or ads of other types have a different set of attributes. The HTCondor manual describes the complete set of attributes for each ad type, their meaning, and their units. Let's run through some quick examples of these non-job ClassAds and see how you might use them. Just like the CondorQ-L command shows all the active jobs in the long ClassAd format, Condor History does the same thing for jobs which have left the queue. HTCondor ages these out after a while, but usually keeps a lot of jobs in the history file, so the output may be huge. We'll use this example Condor History-L output to show some examples. Note that these ads are still jobs, and so have most of the same attributes as them as active jobs. One attribute that active jobs don't have often is last remote host, the host name of the last machine this job ran on. Active jobs have a remote host when they are currently running, but they don't usually have a last remote host attribute, and that is until the exit. Condor History takes an optional -AF option, just like CondorQ, to do a projection out of some attributes. Here we project out just the last remote host to see where jobs have run. And here's an example of a constraint expression with Condor History. We're going to display the job owner for every job in the history that last ran on a machine named A. I've made the machine names as short as possible to fit on the slides. Also, notice the machine names are strings and are quoted as such in the constraint expression. Turns out Joe is the only user who has completed jobs that ran on machine A. Most HTCondor administrators are familiar with the Condor status command, which shows you information about machine slots in your pool. Condor status-L shows the full ClassAd for all the slots in your pool in long ClassAd format, just as CondorQ-L did with job ads. Slot ads, however, have different attributes in them from job ads as they represent the slots in the machine where jobs can run. And here's an example of Condor status-L output. Again, cut down to size with just a few attributes per slot. Typically, a slot will have a couple of hundred attributes, and just like a user can add custom attributes to their job ad, so too an administrator can add custom attributes to their slots. How to do this is beyond the scope of this talk, but it is highly recommended. Typical custom slot ad attributes might be where the machine is physically located, what machine room or rack, what group paid for it, or even the current temperature of the machine room. These attributes I'm showing here include the name of the slot, the amount of memory allocated to the slot, and the current activity, either idle or busy running a job, as a string value. The -AF option to Condor status works just like CondorQ or other tools like Condor User Prio, and in this example we are projecting out the memory attribute, which has an integer type. And if we do this, we show the memory for every slot on our system. And -const works the same as CondorQ as well, although now with the attributes that exist in their slot ads. Here, we want to select the names of all the machines with more than 2,000 megabytes of memory. And this will show just these two slot names here. Constraint expressions on command lines aren't the only places that we use ClassAd expressions. There are a lot of other places in HTCondor that can be customized this way. Let's look at some of the most common places and typical uses for these constraint expressions. Returning back to our job ad example from earlier, we remember that the things on the right-hand side can be numbers, strings, Booleans, or maybe even undefined. But that's not the complete list. We can also have expressions on the right-hand side. maybe something like this. This custom attribute has a value with the expression disk usage greater than 100. This particular attribute is not a standard one in an HTCondor job, but you can add it just like you could add any other custom attribute with the plus syntax in the submit file. That might look something like this. These expressions can in turn return to other attribute expressions and so on, which gives you a lot of flexibility. Remember that options to the shell, like CondorQ or CondorStatus, need to be quoted, but expressions in the submit file are not interpreted by the shell, and thus there's no need for the single quotes around the whole thing. Once we have this expression, we can use it like a function, either in -af or constraint expressions. And in this case, if we constrain with the isDiskHog, we would return no values. HTCondor itself has a lot of predefined expressions that it puts into ClassAds, both job and machine. We'll see uses of those in a bit. Let's return to our slot_add examples for a moment. One of the predefined attributes in a slot_add is has_avx, which tells us whether this machine has the Intel AVX instructions. As the AV instructions are relatively new, very old versions of Condor didn't know how to detect them, and thus have AVX is always missing, that is, undefined, for those old Condor versions. Let's say we want to know all the slots in our pool that we know for sure have the AVX instructions. I hope that by now you can write this query, and it should look something like this. There's more than one way to write the query, though, so if you didn't get exactly that same text, you're probably still good. And in this case, slot1 at a.com is our only slot that has the AVX for sure. Let's say that you have a job that can only run on a machine with AVX instructions. You can tell HTCondor to do this by adding a ClassAd expression in your submit requirements. In fact, submit requirements are probably the most common place HTCondor users put ClassAd expressions. Really, what you are telling HTCondor is to select only those machines with AVX as eligible to run your jobs. So, you can use the same expression we just used in the CondorStatus example and put it in your submit file. And then HTCondor will only run your job on AVX machines. So, the bolded text here is what you'd add to the submit file. Again, notice that the shell line needs the single quotes, but the submit file doesn't. HTCondor will automatically add this requirements expression to other constraints it thinks your job needs to build up a full requirements expression. For example, it'll take request CPUs, memory, and disk, and use those to construct a full requirements expression. So, if you look at the requirements attribute in a job ad, don't be surprised to see a lot of attributes that you didn't explicitly ask for. Also, this means that if your job needs a certain amount of memory, disk, or CPUs to run, you should always use the request CPUs, disk, or memory commands, and not try to add them to the requirements expression manually. While submit requirements expressions are the most common way users write ClassAd expressions, administrators most commonly use ClassAd expressions in startd and other daemon policy. The HTCondor administrators talk describes these in great detail, but let's just quickly look at one startd expression, the start expression. This expression selects which jobs this startd worker node is willing to run, and it can be any legal ClassAd expression. The startd start expression, defined in the worker node config file, whose syntax looks a lot like a submit file. Let's say that we want this startd to only run jobs whose owner is Joe. We would just put this into the start expression in the startd config file, and then only Joe's jobs will run here. You can probably imagine all kinds of possibilities in this case. Advanced users can use ClassAd expressions to automatically manage their jobs by adding policy expressions to the job ad. For example, Condor submit files can take a periodic hold expression, which periodically evaluates the given expression, and, if it evaluates to true, puts that job on hold. This is one way to prevent runaway jobs from running forever. In this case, we write an expression to automatically put this job on hold if it starts more than 10 times. See the HTCondor manual for the complete set of policy expressions, including those the administrator can use automatically to put into everyone's jobs. In one of the earliest slides in this talk, I showed how to do a projection with CondorQ and the CondorQ-L and AF options. I said that AF took as an argument a ClassAd attribute name, and while this is true, it's not the complete story. Actually, the AF option takes a ClassAd expression as an argument, because attribute references, the name of attributes, like cluster ID for job, are full expressions in and of themselves. You can think of the expression as a simple kind of, an attribute as a simple kind of expression. So, as long as we quote properly with the shell, we can put any ClassAd expression as an argument to AF. And while maybe this example doesn't seem so useful, you can imagine doing things like converting kilobytes to megabytes, a large number of seconds to a readable number of hours, and other conversions like that. But that's not the most useful use of putting expressions on the command line like this. While it is common to make the argument -af to just be an attribute name, like cluster ID, you don't have to have any attributes or reference any external add at all. And if you combine this with a condor status -limit 1, which means only look at one slot add, you don't just have a very clunky calculator, you have a handy ClassAd debugging technique. For example, maybe you are like me, and it always takes a couple tries to get regular expression syntax just right. This is a good way to test regex with test patterns. Or maybe you've forgotten what undefined == string means. This is a good way to test. And when you write interesting ClassAd expressions, I highly recommend using this technique to debug them. And speaking of debugging, another good debugging technique is to use the ClassAd debug function. Let's say you have a complicated expression in your jobs requirement statement, and it doesn't seem to be working. You can wrap this function in the debug built-in function like so. The debug function takes as its argument, evaluates it, and returns it just like the debug function wasn't there. Thus, debug is a no-op. However, it does have a side effect of writing down some diagnostic information into the log of the daemon that used it. Thus, you'll need read access to this log to see what's going on. Debug is often a tool that administrators like to use. And if we did that, the following would appear in the negotiator log. It shows us that in this case, the custom ClassAd attribute want cluster is undefined, and memory is greater than 1024. And maybe we got the sign backwards in that case. So the expression simplifies to undefined and then false, which is false. Knowing how to use this tool can be a tremendous time saver. New in HTCondor version 8.9 is a standalone ClassAd debug evaluator tool called ClassAd eval. This tool takes two options. The first is a ClassAd, surrounded by square brackets, with the attributes separated by semicolons. There's bound to be shell special characters in there, so you want to escape that from the shell with single quotes. The second argument, which should also be single quoted, is the expression to evaluate in the context of the first add. I think you'll find this a great way to debug ClassAd expressions. After mastering the fine art of debugging ClassAd expressions, we can approach the peak of ClassAd usage, matchmaking. Matchmaking is a special kind of selection that happens in HTCondor, most notably when trying to match jobs to slots. Thus, it's at the heart of the scheduling policies of HTCondor. At the core, matchmaking is just a two-way match. The system takes every idle job and, one by one, tries to find an appropriate slot to run it on. So, it takes one job add and one slot add and checks for a match. If there is a match, the job can run on that slot. If there isn't a match, it keeps looking. The way the match works is like this. The user provides a requirements expression for their job, as we discussed earlier. This job requirements expression must return true for the selected slot add. But that's just the first step. For the two-way match, the administrator also provides a requirements expression, which comes from the start expression in the startdconfig file. If the job matches the slot, we then check the other way to see if the slot matches the job. Only if both sides match do we consider the match valid. This is what we mean by two-way or bilateral matching. And here is an example job add on the left, which we try to match to a slot add on the right. Note that both have a requirements expression. The job has a custom requirements expression saying that it can only run on machines where the administrator has put in a custom ClassAd attribute, has MATLAB license, and that has to evaluate to true. This is not something the HTCondor detects, but it's the sort of thing very common that administrators add as custom slot attributes. Also, the machine has a requirements expression that came from start that the administrator defined. In this case, it only wants to run jobs submitted by gthane and those jobs from him that haven't restarted more than 4 times. First, HTCondor takes the job adds requirement. Much like the -constraint option to condor status, we check to see if it evaluates to true. Because the slot does define has MATLAB license as a true value, this requirement expression is true. And as that was true, we then check the other side. The slot requirements expression also evaluates the true in this case, so we have a successful match. Now, in the greater Condor world, this doesn't guarantee the job will run on this slot. Maybe more than one slot match, and maybe there's quotas or other things going on. Other talks go into great detail about how the full scheduling works, but the first step is always to make sure there's a match. And here we have When matchmaking evaluates each requirements expression, it may look just like the constraint expression in a CondorStatus status or CondorQ command. But there's a little more going on here. In particular, when we were running those command line tools, we were always evaluating that expression against one ClassAd at a time, the slot adds in the case of CondorStatus, job adds in the case of CondorQ. We might walk through a big set of those adds, but fundamentally we were trying to check one expression against one add in turn. But with matchmaking, we always have two adds, the job add and the slot add. And when we have two adds, something a little bit different happens with attribute reference lookup. Remember that HasMATLAB license here is an attribute reference lookup. But in matchmaking, we don't just look at one add for the attribute, we look in both adds. First in the add we started with, the job add, and if MATLAB license isn't there, then we'll look in the other add, the slot add. And the same happens when we try to evaluate the slot adds requirement expression. All of the attribute references are first looked up in the add they came from, the slot add now, and if they aren't found there, look in the other add, the job add. Here we have two attribute references, owner and numJobStarts, and they both live in the job add. We can use this to our advantage by giving names to otherwise magic constants. In this case, instead of having the slot add say numJobStarts is less than 4, we can say numJobStarts less than max tries, which we define separately in the slot add. This is more clear, and while max tries is a custom attribute, we could also use this to refer to other built-in attributes. To be clear about which add is which when matchmaking, we call the add we got the requirements from the myAdd, and the other add the target add. So when we evaluate the job add is the myAdd, and the slot add is the target add. Conversely, if the first part of the match succeeds, and we are trying the second part by evaluating the slots requirement, then we call the slot add the myAdd, and the job add the target add. Often in matchmaking, you don't want class adds to look up in both places. In the max tries example, you know that max tries should be in the slot add. That's the myAdd. If it isn't there, it probably should be an error, and you don't want the user to be able to override your policy by defining their own max tries. So, when matchmaking, attribute references like max tries can have a prefix which tells them to only look in one add. These prefixes are my.dot and target.dot, which tell class adds to only look in that add, and if it can't find it there, return undefined instead of looking in the other add. So, we can change max tries to my.maxTries. Similarly, if you know that an attribute reference should never be found in the myAdd, only in the target add, you can use the target.dot prefix. This will cause class adds to only look in the target add, the job add in this case. So, we can change owner to target.owner and numJobStarts to target.numJobStarts. In general, adding target.dot won't impact the correctness of a class add expression, but it does help to convey intent to other human readers. I strongly recommend using my.dot and target.dot prefixes in as many places as possible as a matter of documentation. Beginning ClassAd users often omit them, but you should always have them. It makes your expressions just that much easier to read. And with that, we've covered matchmaking and the end of the basic ClassAd tutorial. I hope that you remember the three main uses of ClassAds in HTCondor. First, ClassAds describe all entities in Condor. Second, ClassAds have a query language that lets you select out some adds from some larger set. And third, ClassAds support bilateral matching of machines to jobs. Now, I have a few more slides about expert-level use of ClassAds. Would you like to hear them? Hearing no objections, we'll move on to a few expert mode topics. These are a potpourri of random, unrelated features that experts find handy in ClassAds. The first is the JSON format output. While CondorStatus-L is the long native format of ClassAds, we can also format ClassAds in the JSON language by passing the -JSON option to CondorStatus or CondorQ. This can be useful for commands that parse the output of Condor command lines. A handy new ClassAd built-in function recently added in HTCondor version 8.9 is the replace and replace all functions. These replace regular expressions with strings and return the resultant string. Remember that the regex function returns true or false, depending on whether it matches. Replace and replace all return the string. One rarely used ClassAd value is a collection type called a list. A list is an ordered set of other ClassAd values. The only current use in HTCondor for ClassAd lists is in partitionable slots, which have lists of attributes of their child slots. This list syntax is comma-separated values, all enclosed in curly braces. The square-based syntax can be used to pull out or extract an individual item from a larger list. Here's a common tricky problem. Let's say you have job class ads like listed in the box here. Note that they all have a requirements expression, and some of those requirements expressions refer to a custom class attribute called hasNFS. How would you run a CondraQ query to select only those jobs which reference hasNFS in them? Now, you might think something like this would work, to do a regular expression match against requirements. But that doesn't work. And it doesn't work because requirements is not a string. Requirements is an expression. So we need something to turn an expression into a string. And that's what this unparse function does. It turns an expression into a string, which can then be used by any of the string functions in Condor, including the regex function. The final subject I want to cover in this talk are the strict equality operators. These are very frequently misused and are almost always the wrong thing to do. But we do see them often, so I want people to be able to recognize them when used, even if they aren't being used quite correctly. As you know by now, class ads have an undefined value and an equality comparison. For example, if you compare a string to undefined, you'll get an undefined value. But sometimes you don't want that. You want a string comparison to undefined to result in false. And that's what the strict equality or exactly equal operators do. They're typed equal question mark equal and equal exclamation point equal. When you use the strict equality operators, undefined loses its special nature. So some string equal question mark equal undefined returns false. Also, equal question mark equal is case sensitive, because it means exactly equal to. And while normal double equal does type conversion, meaning that integer 42 is equal to floating point 42.0, the strict equality operators do not do this conversion, and that operator would result in false. All in all, my advice is not to be afraid of undefined, and only use the strict equality operators if you absolutely need to. Usually, propagating undefined throughout your expression is the right thing to do. And with that, we're at the true end of this talk. For more information, please check out the manual at htcondor.readthedocs.io, or subscribe to the HTCondor users email list, whose subscription information is found under the main HTCondor webpage at htcondorproject.org. Thank you for your time, and I hope you enjoy using ClassAds.